Okay, right now we're going to take a look at the dry ice scenarios we did in class. So I've got a little sketch here of the table that we used with a little red line on there to indicate the little purple line I used in class as the 0 position. So the dry ice was sitting on the table. Well, let's say this is scenario 1. So scenario 1, we had the dry ice. It was just kind of sitting there in the center of the table, and it was at rest, motionless. So we'll say at rest in the center of the table. And we had talked in class about making a force diagram for the piece of dry ice. And we also talked about a motion map. So a motion map and a force diagram for the dry ice, which is at rest. So the force diagram, we indicate the piece of dry ice and represent it by a dot. And now we need to draw the forces that are acting on the dry ice. And how we do that is I would draw one arrow in the downward direction, and the force that's acting in the downward direction is the force of gravity. So we would actually name it force of gravity on ice. There's an upward force also on the dry ice, and it's the same size as the force of gravity, and we call that the force of table on ice. So the fact that these two forces are the same length mean that this force of table on the ice, upward, force of gravity on the ice, downward, are equal amounts, opposite direction, and so we would call these balanced. So these are what we would call balanced forces. Boy, this writing is terrible. Hopefully you can read it. Balanced. And so the motion map then would look like this. If we mark out the 0 position and the positive direction, my dry ice would be doing something like this, showing that it is staying at the same position, meaning same position as measured from the 0 over, same position, for multiple seconds in time, and we would also say that the acceleration is 0, because again, it is at rest, it is not accelerating in any way. All right, if we go to the next scenario, scenario 2. Scenario 2, we have the dry ice here, and it's actually moving with a constant velocity across the table. So, constant velocity is what it was doing in class. So, if we look at the motion map, I guess I'll start with the motion map this time. We would draw that with arrows that are all the same length, starting at least near the 0 position, traveling to the right, constant velocity, constant length arrows. And then we would say that the A is 0 here as well because there's no acceleration. Now in terms of the force diagram, we look and we obviously know that gravity is acting on the dry ice in the downward direction, and the table is still acting on the dry ice in the upward direction. So we'll draw those in like we had before. And again, I might start abbreviating now to save a little bit of time and space. Force of gravity on ice and force of table on ice. Now, the tendency is to want to put another force in here, somewhere over here, because there's movement to the right. And so most people think, well, there's got to be another force here. But there is no other force. We only have two kinds of forces. We have contact forces and field forces, and neither of those are showing up right now. So we have no force here to the right or the left in this case. Friction is so small we ignore it because it is a piece of dry ice floating on a cloud of itself, essentially. So, no force to the right, no force to the left, and again, we have 0 for an acceleration. And again, we would call these forces balanced. In fact, it's the same force diagram that we just had on scenario 1. And so we'll move to scenario 3. So scenario 3, again, we have the dry ice. And in this case, the dry ice was moving to the right. And I'm going to draw in here, this is the force probe I used, which was, if you remember correctly, a playing card, the ace of spades, I believe. And the dry ice was moving in this manner. Notice I have arrows that are getting longer to the right, so speeding up to the right. So if we look at the motion map, indicating which direction is positive, so it started at the 0 position, not very fast, and it got faster and faster as time went on. And that means our acceleration then is to the right. Again, knowing that when it's moving to the right and it's speeding up, the acceleration is in the same direction as the velocity. The motion, or the force diagram, rather, how is that going to look? Well, again, we still have gravity acting downward. We still have the table acting up. So force a table on ice, and again, I'm abbreviating even more now, force of gravity on ice. Now, we do have, in this case, the force probe, or the playing card, is pushing on the dry ice to the right. So we will draw that force in. There is a force acting to the right, and we would call it force of probe on ice. And so we notice here, there is a force to the right. This up and down, we have balance. Right and left, we do not have balance. So we would call this then unbalanced. And we'll notice that the unbalance is in the direction, same direction as the velocity, or the acceleration rather. So the acceleration and the unbalanced force are in the same direction. Not a coincidence. And we'll move on now to 4. So scenario 4, we had the dry ice that was moving actually to the right and was being slowed down because I had the force probe this time acting on the opposite side. So we had slowing down. On this scenario, slowing down as it moves to the right. So if we look at the motion map again, starting off with long arrows because it was moving quickly, and those arrows are getting shorter because it's actually getting slower and slower, and eventually it stops. Now the acceleration then would be in the negative direction to the left, because whenever it's slowing down, the acceleration is in the opposite direction of the actual travel, or the velocity. Now the force diagram, again, we still have force of gravity on ice. We still have force of table on ice. And now, if we look at the picture again, the card, or the force probe, is on this side. With the ice moving this way, the card is pushing to the left to slow it down. So that means when we draw our force in, we're drawing it this way. That is the force of probe on ice this time. And you'll notice again that if we look at the direction of our imbalance. So the unbalanced force now is to the left, and you'll notice our acceleration is to the left. So in this scenario, we now have unbalanced, again, well, let me use the pen, unbalanced forces. And unbalanced forces, again, are resulting in an acceleration in the direction of the unbalanced force. So what conclusion can we draw here? Well, things down. First of all, let's get the pen again. Balanced forces. What do you get when you have balanced forces? Well, you don't get an acceleration. No acceleration. So what are your options then? If there's no acceleration, then what do you have? Well, you could have an object at rest, or you could have an object at constant velocity. Either way, you don't have acceleration. All right. So what's the other option? Well, you could have balanced forces. Unbalanced forces. If you have unbalanced forces, what does that mean? Well, according to the force diagrams that we've had and the motion maps we've had, if you have unbalanced forces, you will have acceleration. And more than that, what will you see about the acceleration? It will be in the same direction as the unbalanced force. So those are some of the conclusions we were able to draw from the dry ice buzzing around and sliding around on the table in class. Hopefully this has helped kind of tie it all together for you. These here are the two huge ideas that we have from this unit. Those are what are going to drive all of our interpretations of the different scenarios that we look at, trying to figure out what kind of forces we're seeing based on whether we see no acceleration or whether we see an acceleration. And that will inform us as to what kind of scenarios we are looking at. Hope it helped.